Given the generalized uncertainty principle for any two quantum mechanical operators, something like sigma q squared sigma r squared is greater than or equal to 1 over 2I times the commutator of the operator q and the operator r, all squared, you might think that uncertainty principles have been pretty well settled. But that's actually not the case. While this does give a good and satisfying explanation of something like the classic sort of delta p delta x is greater than or equal to h bar over 2 sort of uncertainty relation, it doesn't cover the case delta e delta t is greater than or equal to h bar over 2. If you've seen this sort of uncertainty principle, it's also very useful in physics, but it is of a fundamentally different nature than position momentum uncertainty. And the fundamental reason for that is that there's something special about time. Time in quantum mechanics is a parameter that shows up in the arguments to your equations. It's not so much like momentum where there's a well-defined momentum operator. So how can we handle energy-time uncertainty? Well, the notion of time in a quantum mechanical system is a little bit squishy. If you're talking about the time evolution of something like e to the I e t over h bar, that solution to the time-dependent Schrodinger equation, or at least the time part thereof when you apply separation of variables, this thing just rotates around in complex number space. It doesn't actually change the fundamental nature of the solution unless you have some sort of a superposition of two states where they have different time dependences, two states of different energies, and the overall time dependence only ever depends on the energy difference. Now, that suggests that if we're talking about some sort of a change in a process, some sort of a change in expectation value of position, for instance, that as it results from a superposition of two stationary states with different energies, we ought to consider the notion of change. Time is only ever going to be relevant when we're considering things that change, because if nothing is changing, then what does time really mean? Well, if we're talking about change, we're talking about some sort of an operator, because we're talking about something that changes. We need to have an observable, so we need to have some operator, and as usual, I'll call that q hat, meaning the Hermitian operator that corresponds to some sort of quantity q. So let's consider time derivative of the expectation value of q. This gives us some sort of classical almost notion of how things change with time. Now, the expectation value in our generalized linear algebra formulation is a linear product of our state psi, our operator q hat acting on state psi. This inner product has three components to it. We've got a wave function on the left, an operator, which potentially has time dependence in it itself, and another wave function on the right, or another state on the right. And if you think about the inner product as written out in terms of an integral of wave functions, this is going to be a complicated integral, but it's got three things in it that are all going to potentially vary with time. So let me sweep some of the mathematical details under the rug here and rewrite this, more or less applying the product rule. So we've got a partial derivative of psi with respect to time, whatever that state may be, multiplying our inner product with q acting on psi. We have psi on the left, acting on a partial derivative of q hat with respect to time, whatever that may be, that operator acting on psi, and we have psi acting on, or inner product with q hat acting on partial psi, partial t. Now this is a very suggestive notation. It feels like it's only ever going to be relevant if we're talking about psi as functions of time. What on earth does this notation mean to begin with? Not much, to be quite frank with you. There's a lot of somewhat dicey mathematical things that have happened behind the scenes in applying the, quote, product rule, unquote, to this sort of expression. If we're really going to write these things out as integrals, then these are well-defined mathematical operations, and you can apply the product rule, and all of these sorts of things make sense. But if we're trying to do this in general, I've kind of swept a little bit too much under the rug. That said, I'm going to leave things in this general form. And the reason for that is it's a much more concise notation. So if you want a sort of behind-the-scenes idea of what's going on in each of these terms, try and translate it into an integral and figure out what exactly has happened in each of these steps. If you're willing to take me at my word that this is at least somewhat meaningful notation, we can write down, for instance, some of these terms with partial derivatives of psi in them can be simplified with the time-dependent Schrodinger equation. And the time-dependent Schrodinger equation tells us that I, h bar, partial psi, partial t is given by the Hamiltonian operator acting on psi. So really I ought to say this is a state, and this is a state in my vector notation. But in this sort of context, you can simplify this sort of term and this sort of term. So let's do that. Let's substitute in for this and in for this. When you do that, these three sort of expectation value-like terms can be simplified a little bit. First of all, this partial psi partial t on the left, I've got a 1 over I h bar when I simplify to just get partial psi partial t by itself. So this is 1 over I h bar Hamiltonian applied to psi as our replacement for this overall state here on the left. And then I've got q hat psi on the right. This middle term here is just going to be the expectation value of partial q partial t. Now, what on earth is that? Can I take the partial time derivative of an operator? Yes, if the operator has explicit time dependence. If the operator doesn't have explicit time dependence, then it's not going to have any partial time derivative. This term is going to be 0, and we're about to say this term is equal to 0 in a few minutes anyway. To give you an example of a situation where this term would be non-zero, think about something like the potential energy in the harmonic oscillator, where the spring constant of the harmonic oscillator is gradually being tuned. The frequency of the oscillator is changing with time. Perhaps the spring is getting gradually weaker, or the temperature is changing, affecting the spring constant. Under those circumstances, this term would be non-zero. The operator for, say, the potential energy in that quantum harmonic oscillator would be a time-dependent operator, and taking the partial time derivative would give you something that's non-zero. This third term, we can also apply a simplification. We've got psi on the left. We're not going to touch that. And on the right-hand side, we've got, let's see, 1 over I h bar. We've got a q hat and an h, and a 1 over I h bar there, acting on psi. Now, the next step in the derivation here, in considering how we can possibly simplify this, is we've got a term with qh bar, or q hat, h hat, excuse me, on the right, and a term here, h hat and q hat. So let's see if we can simplify this by applying the notion of a Hermitian operator to each of these terms. If I use the fact that h hat is a Hermitian operator, I can simplify, or not simplify, I can move the h. I can, instead of having h act on the left, I can have h act on the right. So this will become an h hat q hat acting on psi, similar to my q hat h hat over here. Now the other thing that I have to do in order to simplify these terms is to figure out what to do with these constants. Multiplication by a constant on the right does nothing. I h bar in the denominator, I'm just going to move that outside. So that will become a 1 over I h bar outside this expression. Now the 1 over I h bar here cannot simply be moved outside, and the reason for that is it's inside this left-hand side of the equation. So if I move it outside, I have to think about taking complex conjugate. So if I'm going to move this guy outside, I have to stick a minus sign on it because I've got an I in it. I have to flip the sign on it. Now if I do those two simplifications, first I have a minus 1 over I h bar. In this term, I have psi h hat q hat psi. This term, which I'm going to write next, is plus 1 over I h bar psi q hat h hat psi. And my remaining term over here is partial q hat partial t, expectation of that, whatever it may be. Now this overall expression here can be simplified even further. Here I have a h hat q hat and a q hat h hat. If you're seeing a commutator on the horizon, you're thinking the right thought. Let's combine these two terms together, these two expectations together, essentially factoring out the psi on the left and the psi on the right. What we're going to be left with is something like minus 1 over I h bar psi, and then the operator here is going to be h hat q hat minus q hat h hat. Factored out a second minus from the q hat h hat term here. And I've got psi on the right. And as before, I've got my expectation of partial q hat partial t coming along for the ride. So this term, now I can write that as I over h bar. If I multiply and divide both of these things by I, basically move the I to the numerator, flips the sign. I have here the expectation of the commutator of h and q, plus the expectation of the partial derivative of the operator q hat with respect to time. So this is a somewhat general result. Any time derivative of an expectation value is going to be given by a commutator of that operator that gives you the expectation and the Hamiltonian, plus some sort of explicit time dependence. If there isn't any explicit time dependence in this, what this tells you is that if the operator and the Hamiltonian commute with each other, if the commutator is 0, in other words, if HQ is equal to QH, then there is potentially going to be no time dependence for your expectation value. Essentially, time evolution of system as given by the time-dependent Schrödinger equation, essentially ignores the expectation value of the operator that you're considering. It's some sort of a conserved quantity. That's a very useful sort of thing to be able to figure out. So if you've got commutator is 0, you're going to have a conserved quantity. Keep that in the back of your mind. Now, for the special case where the partial derivative of the Q operator itself is exactly 0, then what we're left with from the previous slide is that the time derivative of our expectation value of Q is equal to I over h bar times the expectation of our commutator h hat q hat. That was our general result. I just dropped the partial the expectation value of this sort of term. Now, back to the notion of uncertainty. If I have the Hamiltonian and my operator q as the two things that I'm considering, meaning I'm looking at an uncertainty in the Hamiltonian squared and the uncertainty in my operator q squared, this is going to be our energy uncertainty. What is sigma q going to be? Well, given this expectation of a commutator, that's the sort of thing that appears on the right-hand side of our generalized uncertainty principle. We had a 1 over 2i expectation of a commutator applied to this particular operator pair is going to be h hat q hat inside the commutator, all squared. So expectation of a commutator, I can rewrite that in terms of the time derivative of the expectation. So my right-hand side here, I can rewrite in terms of this as I've got my 1 over 2i as before. I got to solve for the commutator by multiplying through by h and dividing by I. So I've got an h bar over I on the left-hand side and d dt of the expectation value of q. All of that's going to be squared. So simplifying this, I've got an I and an I, which is going to give you a minus 1 in the denominator, so I'm going to have a minus sign, but I'm squaring everything overall, so that's not going to change much. And what I've got for my right-hand side is h bar squared over, let's see. Let me write it as h bar over 2, quantity squared, and then I've got my d dt of the expectation value of q squared. So what this tells you is that sigma h, sigma q, taking the square root of both sides of this equation, is going to be greater than or equal to h bar over 2 times this weird thing, the time derivative of the expectation value of q. I'll put that in absolute magnitude sign to cover my bases in terms of square roots of squares. What this tells you is that the uncertainty in the value of an operator, the uncertainty in the operator itself, is going to be related to the time derivative of the expectation value of that operator. Essentially what that's telling you is that your uncertainty in the outcome of a measurement is going to depend on how quickly the quantity that you're trying to measure is changing. And that seems honestly rather logical. There is another factor here in terms of the uncertainty in the energy that helps bring things into focus further, though. So let's make a note of this result. It's nice and sort of qualitatively appealing, the notion that the uncertainty in an observable is related to how fast it changes, and the more quickly it's changing, the higher the time derivative of its expectation value, the larger the resulting uncertainty must be. But let's see if we can cast that in terms of that classic delta E, delta T uncertainty. if we're talking about delta E, that's essentially our sigma sub h. It's our uncertainty that results from a measurement of the energy, which is given by proxy in the notion of quantum mechanics, or the language of quantum mechanics, in terms of the Hamiltonian operator. And really we need some notion of delta t as well. What is delta t in this case? Well, let's define delta t to be something like the uncertainty in our observable Q divided by the magnitude of the time derivative of the expectation value of Q. This is sort of some characteristic size of change in Q multiplied by the rate of change in Q. So if this is some sort of delta Q over dq dt, this would give me some sort of a notion of delta t. More by dimensional analysis than anything else. Really what this means is sigma q can be thought of in terms of the time derivative of the expectation value of q and delta t, if I just say multiply this out onto the left-hand side, which says that this characteristic time that I'm interested in is the amount of time it takes the system to change by one sort of standard deviation of the observable in question. So this is going to depend on the observables that you're working with in some sense, but it is a notion of the characteristic timescale of change in the system. Now under these circumstances, our sigma h, sigma q expression is going to look like h bar over 2, and then we had the time derivative of the expectation value of q. That is going to be converted into delta E, replacing sigma h, delta t, replacing sigma q, with this sort of expression. And then you can cancel out, essentially, this time derivative of q is going to appear both on the left-hand side and the right-hand side, thinking about it along those lines. And what we'll be left with is just that this is greater than equal to h bar over 2. So, there you have it. We have a derivation of the conventional energy-time uncertainty relation. What you should keep in mind here is that all of this was derived assuming a particular observable. So the potential results that you're going to get are going to depend on the quantity that you're interested in. If some quantity that you're interested in is changing very rapidly, then you're going to end up with a relevant delta t. This delta t is not just some time measurement uncertainty, it's a timescale of change of the quantity that you're interested in. So there has to be some sort of quantity in the back of your mind. You're not just saying delta t for the system, you're saying delta t for momentum, or delta t for position, or delta t for kinetic energy, or something like that. Regardless, the conclusions are the same. The system is evolving rapidly, meaning with respect to the variable that I'm concerned about, the time derivative of the expectation value is large. Then what that means is that delta t will be small, right? Large number in the denominator gives you a small number. And what that means is that the uncertainty in the energy will be large. Essentially what that means is if you have a system that is changing rapidly, it has to consist of a superposition of a wide range of different energies. You can only ever get a system to evolve rapidly with time if it contains a wide range in energies. And that gets back to the same sort of discussion we had earlier on in this lecture, where I said that the only way you ever got an expectation value to evolve was if you had a superposition of states with multiple energies. The wider the separation between those energies, the more rapidly the evolution would occur. That's reflected again in this energy-time sort of uncertainty relation. The flip side of this, if the system is relatively stable, what that means is that your system is evolving slowly with respect to the observable that you're interested in. So the time derivative of the expectation value of that observable is small. Then that means it will take a long time for the observable to change by one sort of standard deviation in the observable, which means our delta t is large. And consequently, our delta E can be small. We can have a small uncertainty in energy if we have a slowly varying system. If you have a system that's stable with time, nothing is changing very rapidly, then the energy uncertainty can be small. It can have a very precise energy. Keep in mind, these are all just inequalities, so you can have a very large energy uncertainty and a very rapidly evolving, and a very slowly evolving system. But at any rate, the last thing that I wanted to mention here is that all of this is really valid for any sort of Q. So this Q is representing any observable. What that means is that if anything is changing rapidly, then the energy uncertainty will be small. We can flip that statement around and say that if the energy uncertainty will be large. We can flip that statement around and say if the energy uncertainty is very small, meaning we're dealing with sort of a determinate state, something with almost no energy uncertainty, then all time derivatives of expectations of any observable are going to be small. And we've said that before in the context of stationary states. Stationary states are the states that are eigenstates of the Hamiltonian operator. They evolve with time in a very simple way, and for a system that is in a single stationary state, the energy uncertainty is zero. Therefore, the delta t has to be a very, very large number, effectively infinity, in order for this inequality to hold, which means all changes in the system take place on a very, very, very long timescale. Everything is evolving very, very slowly. And in the sense of a true mathematical stationary state that is exactly stationary, nothing is allowed to change with time. Stationary states are truly stationary. So, that wraps up our discussion of energy-time uncertainty. This is fundamentally different than the notion of position-momentum uncertainty, where both position and momentum are operators. But it does have some nice general interpretations in terms of the rate of change of expectation values of operators. So keep all of this in the back of your mind. It will help you interpret the behavior of quantum mechanical systems in general as they evolve with time. Momentum operator. So how can we handle energy-time uncertainty? Well, the notion of time in a quantum mechanical system is a little bit squishy. If you're talking about the time evolution of something like e to the I e t over h bar, that solution to the time-dependent Schrödinger equation, or at least the time part thereof when you apply separation of variables, this thing just rotates around in complex number space. It doesn't actually change the fundamental nature of the solution unless you have some sort of a superposition of two states where they have different time dependences, two states of different energies, and the overall time dependence only ever depends on the energy difference. Now, that suggests that if we're talking about some sort of a change in a process, some sort of a change in expectation value of position, for instance, that as it results from a superposition of two stationary states with different energies, we ought to consider the notion of change. Time is only ever going to be relevant when we're considering things that change, because if nothing is changing, then what does time really mean? Well, if we're talking about change, we're talking about some sort of an operator, because we're talking about something that changes. We need to have an observable, so we need to have some operator, and as usual, I'll call that Q hat, meaning the Hermitian operator that corresponds to some sort of quantity Q. So let's consider time derivative of the expectation value of Q. This gives us some sort of classical almost notion of how things change with time. Given the generalized uncertainty principle for any two quantum mechanical operators, something like sigma q squared sigma r squared is greater than or equal to 1 over 2i times the commutator of the operator q and the operator r, all squared, you might think that uncertainty principles have been pretty well settled. But that's actually not the case. While this does give a good and satisfying explanation of something like the classic sort of delta p delta x is greater than or equal to h bar over 2 sort of uncertainty relation, it doesn't cover the case delta e delta t is greater than or equal to h bar over 2. If you've seen this sort of uncertainty principle, it's also very useful in physics, but it is of a fundamentally different nature than position-momentum uncertainty. And the fundamental reason for that is that there's something special about time. Time in quantum mechanics is a parameter that shows up in the arguments to your equations. It's not so much like momentum where there's a well-defined momentum.